get this going. So there we are. I feel like so I completed my Cambridge half marathon, survived that. If you won't see me walking around too much, stay right here. But we'll try to be interactive. So, that said, let's go ahead and get into networking, and then networking in the sense of the topic, and also hopefully with your team members. So you will be, moving around a little bit today. Fine, folks. So. Since we're starting with networking, just wanted to start off with some interesting, or what I found interesting, pre-warm-up here, just about the internet. There's 32 mind-boggling facts or whatever from this article, but just a few that were sort of interesting as far as just how much content that we consume. So a zettabyte of bandwidth. So 1 zettabyte is equal to 1,000 exabytes. That's something bigger than a petabyte, and then we finally get down to terabytes, so just for a scale. So that's a lot, I guess, and growing. And the prediction was in 2016 by Cisco, the sort of cloud company or network provider, that 82% of our traffic would be from video, and that sort of makes sense. YouTube, streaming services, and so on. That's where we're passing along a lot of data. But one that I thought that was kind of funny was, so of course, folks are familiar with Gmail, but little did you know, Gmail.com was first owned by the folks Garfield and Friends, the comic. So it was Garfield Mail. They had a email service. I don't know how they got into that pivot, but eventually Google said, hey, we want that domain, and bought it. But little did you know. So I thought that was kind of cool. If you're not familiar with Garfield and Friends, is an American comic. It's about a cat, Garfield, and you can read this. So the next time I see you two, I expect you'll be doing something worthwhile. So you know what that means, don't you, Odie? That's a dog. We'll never see John again. It's the kind of dog. But anyway, so I actually did look, since it is 2021, to see if Cisco's prediction is true. I can't believe it's 2020. It feels like 2019, sort of. So I don't really know what year it is. It's one sort of weird thing for all of us. But so I was looking, and the only articles I could find were more about this prediction. So I don't think anyone's accounted for this yet, but it might be interesting to see when they do come with those numbers. What Zoom and these sort of things did to internet traffic. If it's sort of, made 90% or something of traffic video, or Disney Plus, or, some of these, huge services that have come out. So that was kind of interesting for networking. So I want to get a little bit into our Scrum, talk some logistics, and then just dive right into networking and show you how we're sort of pivoting a little bit in this course more towards project mode here. All right, so last class, what we were working on a week ago, static analysis and dynamic analysis, so sort of building off our idea of testing and being able to build more reliable software, but relying on tools and this general idea of what can we ask of a program that's sort of, could I divide by 0 here or whatever. So with our static analysis, or dynamic analysis, actually logging what happens. So sort of the difference between those two ideas. In your lab, you got a chance to play around with CPP check as well for your assignment 3s. So maybe folks found interesting stuff, maybe not. I actually wondered, did anybody find useful or changes? Yeah, if you did.
I did find certain mistakes that I made on the assignment,
Yeah.
but then I pushed it. So am I in trouble because
Yeah.
Didn't count for it though.
Yeah. So I mean, as far as like late days, we'll look at it. If we take a late day, just let us know. Like if you went back and fixed something, we won't penalize for that. Yeah. We can grade whichever version of the assignment you want. Yes. Yeah. So there was something interesting though with CPP check.
yeah.
Okay. Yeah. Wondering for other folks, did they find things stylistic or anything in particular? Yeah.
Add on unused variable.
Unused variable, yeah. So even just cleaning up the code a little bit can be useful for that. So eventually, not today because we're talking about networking, but we'll figure out how to integrate CPP checks so you don't have to remember to run the tool or whatever, but you'll always get a report anytime you build your project or try to push to GitHub, which is kind of cool. So CPP checks are a great tool. Oh yeah.
Yeah, there was one thing like there was this flag that you were using earlier, right? So
Yeah.
I couldn't figure out like if you use that flag, it just shows that you have like include elements missing, but like without it, it runs.
Yeah, was it this one, the W effective C++ one? That flag?
There's
Or
a
is it-
CPP check that you mentioned in the lab. I think you ran it in the class as well. So it gave you a bunch
Okay.
of errors, but then we just like do CPP check file name.cpp and it ran.
Oh, right, yeah, because I think I did like enable all or something for all the checks. Yeah, so that may or may not have given you stuff. Yeah, come
So
on.
I figured out the issue with that. It's you have to do -I to tell it where the include directory is.
Oh, yeah. Okay.
And then, but then the other problem is if you have stuff like IOStream that's not in that include directory, it's in some system include directory, then it can't check those include files. But you shouldn't do that because if there's an error with like IOStream, then you have a bigger problem.
Okay, yeah, so a little bit more configuration, I guess, on CPP check. I think you probably truly have to get it to work. You have to pass in exactly what you're using to compile, plus the system pass. There must be a way to do it. That's Piazza Post worthy, I guess. Yeah, comment back.
CPP check prompted me to do the keyword explicit.
Oh, yeah.
In the constructor.
Yeah.
Maybe you could talk a little bit more about it.
Yeah, so there's a nice keyword in C++. It's called explicit. Let me just bring up an example here. And this is actually a good practice. So let's see, explicit, something like this. So if we have some class here, let me see, is this biggest? Okay, can folks in the back see this? Okay, okay. Let me think about a class here. Let's say we have money, for example. And we want to have some constructor for this. Or maybe, how about account or something? Bank account, something kind of generic here. And we want to be able to create this, so some client is opening a bank account, some checking account, and you have your sort of initial dollars here. And let me be, we probably want a lot of precision for this, so a double sounds even better. So what we can do in C++ is if we write explicit in front of this, what will happen, and let me actually just write this out here. See if it'll give us the warning. So here's our class. Let's create a bank account. And then if I pass in some number, 3.1415269 or whatever like that, this will create our bank account. Mike. Let me split this up here. Let's compile it. And let's see, bank account or explicit here. Okay, so this works fine here. Now what if I create another bank account here? Let me just put it in here. I just pass in the number 3 here. Let's see what happens. This will actually give me an error. Yeah, because it needs to be 3.0. It explicitly needs to be a double. So it's not going to automatically convert 3 to 3.0. It's going to say, are you really sure? Is this what you really wanted? Because most of the time that's the default that happens, right? If we, we can do sort of, this is one of our bugs we showed earlier, right? If I have a int here and I call it pi and I say it's equal to 3.14, whatever, right? This will truncate it down to 3 here. If we use explicit, it'll avoid that automatic conversion. So that's usually a good thing to do. Right? If we chose this double, right, we put some thought into whatever this type was. So we might want to enforce that the user actually does that. Explicit's a nice one. Yeah. And I wonder actually, let's see if I, so without compiling this, let's see. Let's just run it with CPP check. So if I get rid of explicit, we do a CPP check here. I guess it didn't give us anything. We have to enable equals all or something like that. Okay, this one says, and here's the actual error. It says class bank account has a constructor with one argument that is not explicit. Okay, so that's what it's investigating there. All right, so CPP check, another great way, in a class like this, even if I was teaching a C++ class, maybe this is what I would teach, but we're never going to be able to look at all the language. You could never cover it all. That's why I like some of these tools, because they really, if you want to get into the nitty-gritty, you can sort of take the time to figure out these as you encounter them. So explicit's a good one. Other thoughts or questions on this? What we were working on last time? The static analysis.
It made me declare the singleton instance as constant.
Let's see. Singleton is
Yeah, it asked me to declare it as constant.
Yeah.
Last keyword was singleton.
Yeah, and that sort of makes sense that the singleton would be const, right? We're not going to repoint it to something else or anything. So that's another good find, right? So my code was not optimal either, right? I need to run it on everything I show now. That's a cool one. Awesome. So any other questions, comments from last week, what we were working on? And then we do have assignment 4 out. From a sort of pragmatic standpoint, now that we have our teams, kind of decided, you're welcome to talk with your teammates as much as you want about assignment 4, because eventually you'll end up merging. I'd like everybody to, complete it, and have it in their repository, but you can talk with your teammates about assignment 4, or if you want to sort of pair program it. I think that's fine. Can't remember if it's this section or the other one where I said I'd make a decision about that. But it makes sense, we're all working together, and all of your code's going to get merged into one repository anyway. So that'll just be for A4. So hopefully folks are making some progress, testing that out, and getting things set up. So just on logistics-wise, again, Lab 7, the next few days, make sure you get that in. For our Thursday section, who's listening in because they're Veterans Day. So Thursday, you don't have any classes, if folks weren't aware. Actually, I might push that deadline to Friday, just since that's a holiday Thursday anyway. But so your Lab 7 will be due shortly. The project is out. I'm going to actually open up the repository. So the repository exists now. So that'll be part of our task to sort of find your team members if they're here in class today, and open up, maybe come up with a team name first and join the repository. And hopefully everyone has a team. If you don't for some reason, let me know as soon as possible. Or if you're on multiple teams. That happened, I think Peter, let's see, I don't know if you're here in a second, but yeah, you were on 3 teams, right? And now you're down to 1. So I don't know. Did you want to do 3 projects? I guess somewhere I decided you were. But, all right, so let's go ahead and take a look at that. Because again, with this sort of shift in the course and where we're going in the project, you'll be working with your teams here. So let's take a look at that. I'm just going to refresh the page here, and we'll see here under week 9. I'll highlight and just point to it here. Project repository is out, so if we go ahead and click on that, that'll bring us just like the monorepo, which we did at the start of the semester, but this time you get to join a team here. So let's see. Okay, my team here. Don't join it. So here we are. We'll accept this assignment here. As usual, give it a moment or 2 to refresh. Then you'll get your team here. And here's the repository, final project repository. I think I may have shown a little preview of this again, but just to give a quick highlight. Again, here's the final project. There's a little YouTube video actually showing the organization of the repository, just so it makes sense. It's going to be nothing more complicated than I'm showing here. But you'll have a labs folder, no more individual assignments, and then just your final project folder. Some places to put your team name, team members, team spreadsheet if you forget, And within this spreadsheet, your specific TA, who's now your project manager. So there's 3 groups for that. So that'll be your first point of contact. It's not that you're explicitly only allowed to visit that person. You can still sign up for office hours or whatever, but this is the person who I'm going to be asking to like sort of pay attention to your repo if you have project questions. They can sort of get familiar with you as well. Let's see. Rubric and stuff, I'll let folks kind of read through that. But what I want to show you is just the 2 different parts of your lab. That'll be pushed to the labs section. That way everybody has it. It's all in one repository. You can all see it. And this is where today's lab is, Lab 8 Networking, which I'll show an example of later. And then the final project here. So it's got a little bit of a README here from your client. So I'll let you read that later. Now, typically the way that I've worked, so I do consulting on occasion. I've been teaching, but you'll get some sort of statement of work, and that's usually your contract if you're consulting. And so you can kind of read this, and it'll have sort of the key items, the proposal, what the objectives are. They're going to be a little bit vague, right? The client doesn't always know what they want, but there will be some deliverable here. So you can kind of read through that and sort of model it after the statement of works that I get here. So let's kind of take a look back one directory here and figure out the logistics. The main sort of important thing here will be to take a look at this milestones link. So here's your milestones. And then you'll notice there are 10 folders here, so there's approximately 10 things to do for the project. I think the first milestone is just to take whatever from your team of 4, assignment 4, and get that into your repository. So that'll be an example of a milestone. Milestone 0, there's actually 11, is to kind of read through this together with your team, make sure you understand stuff. So they vary in sort of range or difficulty. This is sort of how I've broken it up here. Okay, now as far as hard deadlines, there's 3 for the project. So by November 24th, you'll do milestone 4, which is a check-in with your project manager. Okay, we should have milestones, right? Just like runners, right? 1 mile at a time. I'm going to ask your project manager to ask these questions. It's not grading you based off how many check marks, but it just sort of gives everybody a system of, to figure out where they're at. So for example, did you come up with a plan or a timeline? That's sort of milestone 0. Did you integrate your assignment? Did you learn any lessons? How has team member communication been? Is everybody talking? So just some of these, basic questions that you'll see here. All right. So that's the first check-in, or first sort of hard, deadline would be November 24th here. You'll have another check-in December 3rd, again, which is just a few bullet points here because we're getting close to the end of the semester. So has everyone had enough stuff to work on? What's your plan to finish on time? And do you believe you'll finish on time? Which everyone will. And then December 14th is our last class, so that's when we'll try to wrap everything up. And then you also have a teammate assessment form here. So you can take a look at that. That's about 5% of your grade comes from your teammates. Put your name in. What degree you think that you contributed to the project. I want to know if anybody was a superstar on your team, so you can kind of give them kudos. And then the task that you're sort of proud of contributing on the project. You can kind of describe it. And then just any other notes that go in here. So that's that portion there. So you're in control of your grade in that sense. I think that's about it. I'll let folks kind of dig around a little bit in the project directory otherwise. But the main thing for today will be to create this, try to meet with whoever's present in class on your team, and then also to know where the lab folder is, that it's in this final project directory here. All right, and then everybody will get the same grades for their labs and so on. Any questions or comments? Yes. Who creates it? I guess whichever one of your team members first gets to it should create the repository. And then once the team's already there, you can just click and join it. So there might be a little bit of communication, maybe email each other or start a Teams chat or something. If you accidentally create two different ones, just let me know which one to keep. That's fine. Other questions? Team stuff? Yeah.
So then after the current assignment and lab that we have to do this next week, then we won't be using our personal repos anymore?
Yep. Yeah. Consider them done. Yeah. then you can do whatever you want with them in a sense of like if you make changes or want to just do whatever. I guess. Just keep them private. Otherwise, yep.
Will we be able to make this repo public?
Let me think about that. Definitely. So one of the parts of the deliverable is going to be to have some videos and stuff. Maybe. Usually what I've had happen is folks will reach out if they're doing an interview or something, and they'll say, hey, can I make this public or whatever, and then I figure out or make it unpublic for just a month or whatever, and kind of hide it. Yeah. So yeah, if you are going to need the code for some reason, that's we can figure something out. And maybe let me think a little bit about it. I don't think there's anything top secret in here necessarily as well. So and I probably won't reuse this project again. So I'll think about it though. Yeah. Other questions, comments? All right. Well, if more comes up, we'll have a little bit of time after class, and we can chat then. So let's hop back into here. And let's see. Let's move along here. Anything blocking anybody from making progress? They want to discuss C++ stuff, CMake, M1. I think there'll be a little bit of discussion at the start when you join your team. Not all teams, for instance, even if you're on an all Mac team, you might have M1 Macs versus Intel. Some folks might be on Windows, analytics are mixed. So there'll be a little bit of finagling to get your build system. I think that'll be sort of part of the first task. That's one of the sort of interesting parts of software. Well, interesting or frustrating, but sort of getting your project built. But expect that to be a first task. Yeah.
I do have one question. Usually when I do the assignments, with SSL, I always have to put these DLL files into the same folder if it's executable.
Yeah.
How maybe we can try to get past that possibly.
Yeah. So the question was about so you're on a Windows machine there. Sometimes you have to drop in DLLs because that's how you load libraries. That's okay if you're on a Windows team. Just drop the DLLs in your project
So
directory.
I don't have to try to, because the TA told me I might keep a 0 for your assignment next time if you don't time that.
I'll have to look at it. Maybe Piazza post that one just so I can
Okay.
see it.
I don't see any possible path.
Okay, yeah, because one of the ways when you distribute software is to actually dump the DLLs. Again, it's probably not best practice to put it in GitHub. We'll have to take a little look at that.
So they are a binary file.
Because they are a binary file, right, exactly. So usually what you could do, you'd have a build script that just downloads it from SFML, or that would be part of CMake. You can actually download dependencies. So we could talk about that a little bit.
Okay.
For now, just to get things rolling though, with your team, if you're all Windows, just get it built and write in your instructions. That'll actually, one of the milestones will be about writing documentation on how you actually run your project. So part of that is it's the user's responsibility to download SML and put the SML 2.5 DLL here or whatever. That's okay too. Yeah. Other blocking issues from folks? All right, let's get into networking here. So today is sort of a crash course into networking. it's not the full course. Some folks here maybe have taken 5700, and that's great. You can sort of be a leader on your team in that regard. But since we're doing a collaborative painting project, we're going to have to figure out how to get two machines or two processes really just to talk to each other, two or more here. I'll give you sort of a short treatment, and then what the lab is a working sample of, or two working samples of SFML code for networking. Okay, just so you have some sort of reference. And then part of the challenge is figuring out, okay, well, you did an A4, how do you make that sort of a networked version? All right, so starting with the sort of very basics of networking, you start with sockets. These are sort of your building blocks, something called a socket. But what is that? I'll define that in a second. But usually when we have a program, we just have one process here, right? This is our app, or whatever we've been calling the program. And it's just sort of in its own box here. And if you do want that process to communicate to the outside world, you need some mechanism to do that. Again, the fundamental mechanism to do that is called a socket. Okay, so this is what we sort of want our programs to look like. So we have some process. There's this thing called a socket, which is some way to communicate from one endpoint to another. So from one process to some network. Now where this network is, this could be on your local machine, it could be all of Northeastern, it could be all of the world. It doesn't really matter. Just you have one endpoint from your process so that it can communicate information out. If you wanted to implement a really primitive version of a socket, what you could imagine doing is just, without having sockets available, is just having a C or C++ program write out to a file. Right? So you've likely done that in Java, right? You could write out to a text file and say info, and you just kind of keep writing out to that. And then just have another process open up that file and just start reading from the beginning. Right? That's essentially what a socket's allowing you to do, except a little bit more efficiently, not using file I/O to do that. With that in mind, if you wanted to sort of build that really simple socket, right, just opening and closing files, a socket actually is just nothing more than what we say is a file descriptor. So it is just some open file that you can read to and write from. Another way people describe this is just a pipe that you can communicate information to and from. So you've seen pipes in the context of this kind of pipe here, right, where I type in some terminal command and then I do the pipe operator and I grep for something. I don't know, Mike or whatever. But this would be communicating, from this output here to this output here. Okay, so that's what a socket's doing too. This is the other way to think of it. I don't know if anybody's ever done this, as a kid or an adult. It's kind of fun, but two tin cans with a tight string. Right? You're talking to the can, it sort of vibrates along the string, and you can hear somebody. That's exactly the same thing that a socket's doing. It's communication from one endpoint to the other here. Okay. That's all a socket is. Nothing scary. It's actually kind of comforting in a way that's your sort of low-level networking primitive. All right. So our networks, as I mentioned, there's many layers to them. Again, just to give you some, background context into stuff before we just dive into SFML. So that'll be sort of the first bit here. But there's many layers of networking, right? System-wide. So that could be, the whole, server room, campus-wide. We call it local area network, or wide area network. Would be, all of the United States or all of North America, and so on. And this interconnecting of machines here, so like seen in this diagram here, is called the internet, okay, with a lowercase I. And then we know the internet with a uppercase I. That's the thing, we think that when we open up Chrome or Firefox, Safari or whatever. if you want to dive a little bit more into it, there's a really nice video here. It's by this YouTube channel called Crash Course. They do a bunch of sort of learning and educational videos, so you can see that illustrated. Now, popular way, or sort of a model to understand networking with just machines talking to each other is what's known as a client-server model. Okay, so the basic idea where you have one server process that manages all the resources. So to put this into context, we sort of here at Northeastern talk about the Cori servers, SSHing into some magical realm into Cori somewhere. Right, where all of our machines live on our campus and stuff. That's the server that we're trying to communicate from. Okay, and then we're the clients that are connecting to the server and requesting some resource, right? Processing power, compilers, or whatever. So that's how you can sort of think of it. So here it is sort of in a diagram form here. And this is just showing one client and one server. But of course, this could be all of us in the classroom. We're all clients. And what we're doing is we send some request. Maybe it's, hey, can I connect to you? Hey, can I download some file? And the server gets to think about it for a little bit. So it's handling the request to see, are you a valid user? Do we trust this connection? Do I have this resource? And if we do, the server has all the resources, and it'll send a response, which could be, here's the resource, here you go. Or no, you can't have it. Or your password's incorrect. No, you might, whatever their appropriate response is. And then the client handles that response. Okay. Now this actual model here is going to work for us as well in our sort of painting application. Okay, we'll have to think a little bit about what that means here in a moment, though. In one slide you have to think about it. Here it is. So just as a reminder, right, our collaborative paint here, and you can see the different names of people painting here. Here's sort of two ideas on how you can model this. This is sort of one of the things you might discuss with your team. Do you have to write a totally separate server application? Or maybe, on the other hand, maybe the first client that joins is also the server. And that's sort of like a peer-to-peer sort of network. So that's something you'll have to think a little bit about. Today, what you're going to get in the lab code is you'll see all the codes in just one file, but one process ends up acting as the server, one process ends up acting as the client. Then you can share all of your other code that you've written. Okay. But in a sense, you will have potentially a different server application and a different client application here. Okay, so how does the communication take place over a socket? What information is being sent around? And again, this is the kind of cool part when you just think about a socket being this really simple thing where you can send bytes from one end to the other. Is it doesn't matter if you're working across Mac, Windows, for folks who might want to do an iPhone or Android implementation. It doesn't matter. You're just sending bits and bytes back and forth. So as long as each endpoint can understand what those bits and bytes are, you're good to go, right? It's just ones and zeros at the end of the day. But we do have to follow some sort of rule as to how the information is transferred back and forth, and we call that what I'm defining here as a protocol. Okay, so a protocol is just some set of rules that you're following. Then that makes sense. Right? If we want to think about this in terms of how I'm communicating, right, the protocol right now is I'm speaking, in English, so you can sort of understand those bits and bytes as I'm transferring to you. So same thing applies in software here. Okay, so again, what are these protocols going to do? These internet protocols will provide some consistent naming scheme, sort of a uniform format, how the connection's actually handled, where we're connecting to. We're going to talk about the sort of two specific protocols in a moment to figure out, how data is transmitted and if it's reliably transmitted or these kind of things. And then we also have to have our mechanism for the actual bytes. And we call this a packet. So you've probably heard this, or maybe you've even seen or open up on your machine, some thing that's measuring how many packets are sent back and forth. Just sort of curious, how many folks have taken the networking course here? 5,700? Not too many? Oh, awesome. Okay, this might open some doors. You might say, this is awesome. I want to take it. How many folks have taken any cybersecurity courses? Over here? A few, yeah. Have you done anything with packet sniffers, those courses? Yeah. Makes you kind of... Wireshark is kind of the popular tool. Makes you kind of a little scared if you ever go to like Starbucks and connect to public Wi-Fi. Right? So if I said that, there's... if I'm communicating this protocol that everybody understands, right? If I'm speaking to in English and somebody outside the doors, with their ear, listening in, we call that packet sniffing. They can sort of understand what's going on. So there's sort of a good and a bad. For our collaborative paint program, it probably doesn't matter if somebody else comes in and starts drawing or stealing our painting. So we're not going to care about some of these things. But we are going to have to think about what this packet is. Okay, so packet, just to complete the analogy, it consists of two parts here, a header and a payload. And the header contains all the sort of details, if you will. How many bytes you're sending, from where they're coming from where they're going to. Okay, so again, and the analogy is if you write somebody a letter, right, whatever you write on the envelope, that's your header information. The return address, who you are, who you're sending it to, the postage stamp, for how far it's going. That's the header. And then the payload, the second part, that's the actual bytes of information you're sending. Okay, so in your envelope, that's whatever the letter that you write and send to somebody. Okay. So that's a lost art. Handwriting letters. Does anybody do that anymore? I still do it. Handwrite your thank you notes to folks. All right, so that aside, so remember a packet with a header and a payload here. Okay, so how does the actual data transfer? Again, I'm sort of showing my system side of things because I want you to see how it works. SFML is going to make the abstraction a little bit easier, but we still need to know what's going on here. But just the detailed steps, so or can look at this later. So the left side is, I'm calling it just host here, host A. That really just means, this machine here is the host where the data is. So I have some data that I want to send. And within our operating system, there's going to be some special system call that can communicate between a network. Okay, so it's talking with your network card and says, hey, you want this data? Okay, we're going to do that through the socket application programming interface. And then we have to fit everything into some protocol. So here's our packet. We've got the data here. PH just stands for the packet header. Again, we've got to know where we're coming from, where we're sending our data, and how much data we're sending. So we call that a frame. Then that gets copied to your local area network. So whichever router's most close. I'm trying to look in this room. I don't think I see any routers hanging out. I see a missing TV. That was here last week. But maybe there's some wires going there. Oh, okay, up here, yeah. So whenever I'm flipping a slide or whatever, packets are being sent to that device. All the data is being copied there wirelessly. And then our router starts looking at it. Is this a valid packet? Do we understand the protocol? Did Mike write all the names and spell everything right on the envelope for where this is sending? If it is, then the router is able to determine where the destination is and kind of forward along. It's going to go from that router to wherever the next nearest router is and eventually make its way. It's pretty fascinating. You can see how many hops in some of these tools. I call them hops, but it'll be like if I want to send some information to California, it might be only like 5 or 6 hops, maybe a little bit more, but it's not too much. Yeah, question?
You see like virtual software.
Yeah.
Where would they like fall like the OSI model?
On the OSNF. I don't know exactly, but just on this one.
Yeah.
So the router has its own, I guess, operating system, or I mean, it's its own processor, and it can read some type of data that's coming in here. This has its own few layers to it. I think when you take the networking course, you learn about like I don't know how many there are, 5 or 7 layers at one point, and then another few here. Eight or 7, depending on whatever book or however deep you are networking here. Yeah. So yeah, I mean that actual router has some hardware where it's interpreting this stuff. Newer routers, these are programmable, so you can add more protocols and stuff, which is kind of cool. But for now, we can treat it as a black box, so it'll just take the packets in and forward them to the right place. Okay, so then the opposite starts happening. So your machine starts reading in these packets of information, and it says, oh, okay, where were they supposed to go? So it's reading the header. It's got a copy of the data. And you just read the data in, and eventually you have some sort of read or receive operation on the other client's machine, and that's how you get your data. Okay?
How does it know like where it's supposed to go to?
Yeah. So in the actual packet header, it'll have a destination. Now I haven't explained what that is, but part of that's going to be an IP address, right? We sort of heard that the IP, where all of our machines sort of have a IP at Northeastern, and then an address within that. So that's how it can be routed. So it's almost exactly like when you write, your street name, house number, all that information's in the packet header. Yeah, but we do have to decide. I'll show you a live example where you have to specify the IP and then something also called the port address. Because otherwise what would happen if I sort of had no address on my envelope, right? It would just send to everybody, or maybe the first person who got it would open it. And we're not supposed to do that, right? That's a felony. Opening other people's mail. So we want to make sure this gets right. All right. So, and I think that actually gets to this next question here. What if the data gets lost too? It goes to the wrong place. You have a bad packet. The data frame size could be wrong. How do the routers do this? How do we do things securely? Those kind of things I am going to sort of push to the networking course. For this course, I don't care if we're doing things securely. In fact, with SFML, we can't. There's no HTTPS within SFML. The library is lacking a little bit there. But here's a resource if you want to get a little bit more familiar. This actually has some nice little applets and interactive exercises too, just for working with network stuff. Okay, so we know we can transmit information. It's going to travel along in this packet, and our machines, we can rely on them to send the information in the right location. We still have to specify the address. We'll get to that. But I want to talk a little bit more about these different protocols that we have. There's actually 2 sort of popular ones. They're not the only ones, but the 2 sort of most popular sort of families of protocols. But just thinking about our internet, or our uppercase I internet. Okay, again, what we mean most of the time when we talk about go look on the internet. We mean on Google or whatever. The 2 internet protocols, the IP I've given here, our TCP, which stands for Transmission Control Protocol, is going to transfer information reliably, which means you have some guarantee or you get an acknowledgement to make sure that that information was in fact sent. So if anybody's ever sent a text message and has requested a read receipt, for example, I guess if you owned a BlackBerry, I think those always do it by default, but right, that, or even, you know, Facebook Messenger or something, you see when somebody's read your message. So you're like, aha, they read it, they can't avoid me. They know I'm asking, where are you? Right, that's sort of TCP, right? You have some guarantee that the message was sent. The other protocol, so the one I have here, it's called Unreliable Datagram Protocol. You can still send information back and forth, machine to machine, but you don't have that guarantee. You're just sort of sending mail. It's what I guess I'm trying to think of the right real world analogy is. I don't know, somebody who sends you flyers in the mail for their new restaurant. You know, they don't know if you ever read it, but they're just going to keep sending them to you anyway. Is the restaurant open? You know, grand opening, last 5 years. You keep sending it the same thing. But there are sort of different use cases here. So you want to remember TCP, and that's what our internet's sort of built on, right? When you go to a website and it doesn't exist, it'll give you a message that says, "Hey, this website doesn't exist." Right, and you would want to know that, right? You don't want it to be a mystery. And you also want to know some other guarantees that the information you're getting is the right information. Okay, so let me sort of move along from here, just to highlight each of them. So TCP, Transmission Control Protocol, ensures that packets, that is the bytes that you're sending back and forth, are sent with high reliability. Okay, so that sort of means the packets must arrive, or if they don't, you have to be able to find out. Okay, so that's sort of the analogy you're going to get in a networking class. Usually they talk about this handshake thing that occurs. So if I'm talking to someone, I say, "Can you hear me?" And then we first have to, go back and forth and maybe shake our hands and agree that we can be heard. And then we start talking. So it's sort of a back and forth communication first. The other thing with TCP is that the packets of data that you're sending, so when I'm communicating, they have to come in a specified order. In fact, it's guaranteed they have to. So again, if I think about myself just talking to you, it makes sense that in your ears, the words that I'm speaking in order come in order, right? They don't come in a random order, right? That way you can understand what happens. So then it also makes sense that if there's multiple people talking and you're listening, there is still some defined, order that you're receiving all the information. Okay. Okay. UDP, on the other hand, Unreliable Datagram Protocol, means that packets of data may be lost or delivered out of order. So again, it's just sending information as fast as you can, so that the receiver can get that information as fast as possible. Okay. I don't know how to emulate that in our speaking analogy. Yeah.
So say if you're making an online multiplayer game, do they typically want to try to use a UDP or a TCP process?
Yeah, hold on to that thought because we're gonna practice in a second.
So
Yeah.
referring back to the picture you were showing, right? So does that mean it doesn't have a destination?
It does have a destination. So we're sending information. We just never know as the sender if they got the actual message. Let's see. I'm trying to think of the right analogy. If I don't have one prepared, sometimes they come out wild. But yeah, it's kind of like. I guess it's like if I'm selling something in a market, on the street, and I'm just shouting at people. I'm sending out the message. There's a bunch of people, a bunch of ears to sort of receive it. But I don't know if anybody's getting it. Nobody's acknowledging me, right? They're just walking past me. They're trying not to look, I don't want to buy your product. So we're still sending out. We just don't know if the data ever gets there. And that's the sort of trade-off. Or this is the trade-off right here. We say that it's unreliable, but it's fast. Right? It's very easy for me to just shout at you, rather than coming and try to do a very, handshake first. Can you hear me? And then talk. And that's with every message. So every time before we talk, we have to shake hands and agree that we can hear each other. So, ideally the application that you're sending information to knows to be listening and saying, hey, there might be some info coming in. So it'll sort of deal with if the information is lost. Okay. So here's sort of a visual, if it's helpful. The text is a little bit tiny here on TCP, but it's the first arrow saying, okay, first request the connection to the server. Okay, and then the server has to acknowledge and say, yep, you're connected. And then I can send and say, I need this resource, and the server sends back the resource. Right, so that's sort of one request. The UDP diagram here is just saying, I'm requesting data. Both ways, request. And then if the server gets those messages, it says, okay, send back the data. But there's no, handshake or acknowledgement about the message. Okay. So that's TCP versus UDP. So there's a comment here about a particular application asking, what would it use, TCP or UDP? And I want you to sort of think about this in a little exercise here. So I'll give everybody, 10 or 20 seconds per example, or whatever to think, and then we'll share thoughts per application. What do you think is the best protocol? So Netflix, for example. Do you think they're using a TCP connection or UDP? And everybody hold their thoughts, and I'll let you think about it. What do folks think? I'll take answers from anybody, whatever you think, or want to justify.
I was going to say TCP possibly, because the reason is you don't want your frames in that sequence when they're being delivered to the user.
Okay, so the answer is TCP because we don't want frames or packets getting out of order when they reach the user. Yeah.
UDP because with hundreds of thousands of frames in a movie, if you drop one, it doesn't matter.
Okay. Well, maybe we want speed. Maybe was there another thought here? Okay. Yeah. This one's tricky. Maybe I shouldn't have put this one first. The first time I taught this, I was teaching systems, the undergrad one, so almost 5 years ago. And I said, I told the class it was UDP. But this one's got a sort of caveat. And someone rose their hand and they said, no, Mike, it's TCP. Because they, worked at Netflix. So I said, okay, let's take a look here, because if you're sending or streaming, 4K video. I know there's a little bit of caveat. That's why I shouldn't have started this one. But they're using their own custom implementation of TCP that sometimes sends out like an unreliable like UDP. So it's sort of a hybrid. So I don't know who wins. However you answered, you're right. So if you look up Netflix, it'll say TCP, but their own custom protocol. So I should have skipped that one, but everybody who participated is right. Except for me, I was very wrong. All right, how about this one? Gmail. So whether you want to think of it as Google Mail or Garfield Mail. I'll let everybody think about it, and do you want unreliable data protocol or reliable?
I wish I could blame emails getting lost on UDP traffic.
Yeah.
Oh, my homework? I don't know where it is.
Yeah, so I'm hearing I'm hearing TCP, but we want UDP. Imagine the world, yeah.
For all the wrong reasons.
Yeah, so I think this one speaks, right, we want TCP, reliable, in order, right? When you send an email, you want to make sure your words are in the right order, right? All the symbols show up as intended. So yeah, TCP for this one. But again, it's, speed matters. It's not that TCP is so incredibly slow, but we can wait a few milliseconds or whatever extra for that handshake and then the information to be sent. And we want to know, right? We want to guarantee that our email was sent here. Yeah.
Can you configure some sort of TCP service such that, let's say you're sending an email and the other computer received it, can that computer then sends a response back saying this is what I got, this is exactly what you sent, and then if they match up, then that's great.
That's a good question, actually. I think you can do things like read receipts and stuff. Different mail clients will support that. I don't know what checking internally Google is doing to make sure that bytes that are sent actually match. I assume they're doing some simple stuff. Well, hopefully more than simple, but there's some stuff where you just check a parity check. Does the number of ones in the bytes sent, is that odd or even, and you sort of store a bit to that. So most of the time, you can do those sort of checks. But I don't know exactly what scheme Gmail is doing. Do you have an intuition on that?
I think in some cases there are some protocols where they just check the hash maps.
Oh yeah, sure.
Send
A
the hash
checksum.
map, and then you have the key generator, and then they check if the hash maps match. And
Yeah.
stop the complete message to I guess.
Yeah, so I know that's common when you download a file. You'll take all the bits, hash them, and they call that your checksum to make sure that the hash matches. So I wonder if they do that per email. That would be probably a good thing to do. Yeah. Was there another thought on that? Yeah. All right. How about this one? Mario Kart's an online racing game here. Got multiple people, maybe in the range of 8 to 16 folks racing online. What do folks think? I'll let everybody think about it. Thoughts on this one?
Probably UDP. I mean, if it was all TCP, people would probably complain about even more lag than there already is. So probably UDP, just for the speed.
Remember one of the Super Smash Brothers, you were only as fast as the slowest person in the entire game? And that was infuriating. Where you could just send your info as you get it and then let the server deal with it. It seems better for Mario Kart.
Yeah, especially if you have different folks around the world, right? Latency in games, so that's a sort of lag or slow down by delay of sending packets or waiting for other folks. So this is most definitely UDP. Most sort of real-time games are going to be UDP. Now you might be able to mix components. For example, if there's a chat feature, you could send information using TCP if you wanted to do that. But UDP's more than likely. Unless somebody's worked at Nintendo here, who's gonna call me out on it. But most video games tend to be UDP. If they're real-time, fast-paced, speed matters. Yep.
To answer the question, Gmail does do digital signatures to ensure that emails are valid.
They do. Okay, so with every email, there's some checksum or.
There's a little button where you can do show original message, and it shows a ton of different digital signatures and stuff on the message.
Oh, very cool.
It uses SHA-256.
What else would it use? I wish I had invented that.
Great name on it.
Yeah, SHA-256. All right, let's get to one we care about here. Ooh, how about this one? Collaborative paint. Whether you want to think about this as Limnu, the company we're emulating, or what you're building. Thoughts? And I have sort of no right answer. You know, this is what you're gonna have to figure out with your team, if it matters or not. Yeah, just thoughts. Yeah.
I have a quick question about the previous example, which
Yeah.
might be relevant to this as well. I mean, like, the protocol can be UDP, but like the first instance when we establish the connection, so will that be UDP or TCP?
Could yeah. So there could be multiple layers to this. So the comment was that could there be TCPs like when everybody's joining the game to make sure hey everybody's joined before we start right before the race begins. There certainly could be.
And
Yeah.
then there's like a shift of a protocol, then like everything that is sent is just UDP.
Yeah. Yep. That's certainly possible. Yep.
I was gonna ask, like, is there like a way to like split it? So, like, for example, like if your user is like doing like audio and visual, like to switch it to UDP versus just like doing like a normal TCP? Like, is there like a switch it like in a way?
Yeah. So the comment was about is there a way to like switch the protocols or maybe use both at once? And the answer is because you're allowed to have multiple sockets per process. So multiple sort of endpoints. The server, in a sense, is going to have multiple sockets. That's actually going to be something we have to talk about at the end, right? Because we're going to have multiple clients and managing multiple sockets. So one way we can do this is, well, in SXML, you create an object called TCP socket, and you can sort of do that, or UDP socket. And then there's other sort of mechanics we can think about, like having one thread, sort of doing something with sockets, and another thread doing something else. Yeah. I'll let folks simmer on that. Yeah.
So can you receive another socket while, like, for example, you receive two in succession, right? And then you haven't had the time to process one yet. Does it get overridden, or does it get added to the first socket, or does it create a second socket?
Yeah, I guess the way to think about it, so per process here I have here, let me see, can folks see this as a TINF? Let me drop it over here. Right, it's just sort of like the, with the tin cans and the strings, right? So you can have one endpoint here to some other, process 2, or, some other client here. I can have another sort of socket, listening in this way. And I can also, if I just want to have one endpoint per process, there's something called a multiplexer. You have one working as sort of, two different endpoints, so it's sort of swapping quickly. Then your question about like ordering or waiting, we do have to think about, are we blocked here? While listening for from this client or whatever. The multiplexer will sort of, you can unblock yourself, I guess. And those are all going to be things we'll have to think about here. But I think we'll get resolved relatively quick. What do folks think about this for paint? Hey, you want to use UDP, TCP? What would you think? Yeah.
Depends on whether you want to be peer-to-peer or if you want to host it on central server.
Okay.
If you do peer-to-peer, you might want to use TCP.
Okay.
But if you have a central server, you could get away with UDP.
Yeah, so maybe with if we do the true sort of client server, I can just sort of have my server over here, and then a bunch of clients, client 1, client 2, client 3, just sending a bunch of requests, and then every time the server, gets a new draw pixel or something, it just sends out to all the other clients all those changes.
Yeah.
Yeah, I think that would be fine. the design will be fine. Actually, we'll just have to sort of discuss with your team what's important. It might change how you handle some of the things like what it means with undo and redo. Meaning, with TCP, you have a definite sort of ordering of what is received. That said, the server at some point is going to have to order stuff, so maybe the packets that are sent back could be reordered, or have like an actual number as part of that information. It says, this is your history, the first thing that happened, or the second thing. So it'd be something to think about for folks. Or maybe you'll just decide it doesn't matter, you don't care. It's a painting application, it's not critical if, we miss some strokes or whatever. And it's more important that, an artist, when they're in the zone, is not interrupted or has lag.
I think in that case, the only thing that might change is the history where are we storing it, right?
Yeah.
For example, if it's like TCP, then we can directly do the undo from client.
Yep.
But in another UDP, we might have to call the server ping and ask if this was executed, then do the undo.
Yeah. I think some inspiration. Let me put a inspiration here. Let's see. Thinking about undo, redo. Look at Google Docs. I think it might be interesting to see what they do. Sort of another collaborative application. There's a particular data structure Google Docs does that's kind of interesting for history. I'm not saying you have to emulate it, but it could be interesting.
So can you undo whatever the other people has done, or you can undo just whatever you have done?
Yeah, I guess that's the question, right? I don't think I specified anything, so when you come up with your use cases, you'll have to. So part of one of the milestones will be documenting your use cases, like we did one in the lab where we did 5 of them or 4 of them, and I did one. Define what it means when you hit Control-Z. Is it just the last thing that happened or the last thing that you did? Because then you might think about, okay, with each packet, I've got to figure out which user that was. Yeah. And that alone is kind of interesting. Design challenge. All right. All right. Let me give you another visual of the TCP/IP protocol here. I just got a couple of them here. Actually, I might just kind of run through this one here. But again, client-server model. So whichever one of these diagrams exists, they're all almost the same. This one just has TCP/IP this time. All right. So again, we're connecting with some sort of socket here. There's some system call made. And I'll show what some of these low-level calls are in a moment, just so you know what you're using. Goes to the network adapter, and then the process is reversed. Network adapter sends back in the form of a packet. You read here on your server and figure out what that action was. Okay. Let's see here. This is probably a good place to pause. I have another break in a few slides, but we've been going for about an hour, so let's break until 7:20, and then we'll resume talking a little bit more about sockets and then into SFML in your lab. Sure.
So I was trying to check, and I actually got it to work, but so we checked everything, and it says 100% done. It doesn't output anything.
Code must be perfect then.
Was it? I
Yeah.
don't believe it.
Yeah, I mean, there might not be anything that it can immediately find that's wrong, so.
Okay, I wasn't sure. Like I checked like
Yeah.
if it created any text files where I can look at it, like what is wrong, but it
Yeah.
didn't. So
I mean, if for some reason, I mean, you could always try to, like, just create an unused variable here in one of the files just to make sure.
it is doing what it's supposed to do.
Yeah.
Okay.
But I think that's what it should be doing. Yeah. It's like it's looking through everything.
Alright.
Yeah. So should be good.
So I should go from server
I mean, I just know now. Why?
Yeah.
Oh, no.
Yeah, but if it's the undo looks like it should usually undo keyword changes, and you really want to like mess with the errors beyond that. Maybe make it
I fix my bugs.
or erase region. Global. So yeah.
Okay. Mentioned that the trick, which was just move everything. Move like what? All the stuff from bank. So when I don't have to pass any references because I took out all the code and just moved everything into the app. So app.
But do you think that's the right way to do it? Because it becomes difficult when we talk about this kind of things like that everything is just do you want to not do this kind of and then do the process of something else? Because if you don't have the names now then it becomes very difficult to understand something.
Oh, I didn't think of that.
That's why we do it for like
What's that? Yeah. For the most part, yesterday was really tough going downstairs. Just because my knees kind of took a beating.
I really didn't understand the
I didn't train as properly as I should have for this half.
Could you get it working?
Been a runner my whole life, other than this last 2 years, really.
I think you get a huge
I already did
Yeah.
like 100 lines of
I
code.
started lifting weights a lot more aggressively.
Yeah, I just copy paste it all.
Yeah, so, but Cambridge half marathon was a beautiful course. We got to run through the Harvard Stadium, which was super fun.
Do you need like the old one or like the new one?
The old one, I guess, the one that's always open. Sometimes if you put in the stairs, soldiers, I think, like soldiers field.
The one like near the John Harvard statue.
Yeah, I mean it's right off of the.
Yeah, that's the old one.
I guess it's
That's-
technically still the campus.
Yeah, that's like the old sort of like foresty.
Oh
Yeah.
Yeah.
Because like the real one, it's like it looks like a normal car.
Yeah. That one must. Oh yeah, that one's way off in West Campus.
It's like it's like so big, it's like a mile away.
Yeah, it was definitely the old one. Yeah. But that was pretty cool. And it was around the Harvard, like Harvard area, the Charles.
Charles River.
Yeah. And that was really cool. Trying to think what else. We ran around MIT was sort of the start in Cambridge side.
I want to go see MIT because it's so one that was just the last time through here. So like I want to go see MIT.
Yeah, MIT's pretty cool.
It's around the water, right?
Yeah, it's really like
Yeah.
Like I could, it's like they're both like educated. They're sort of like
I just drew a lot.
they feel like a bit like a world apart.
So then,
Yeah, Harvard's a very
So,
beautiful campus.
after
MIT
you,
is very
like,
like.
if you draw after a month, it's supposed to
Yeah.
find out the stats, right? So you can't
It's very
undo it.
Yeah.
Harvard was like really classy.
Yeah, I mean, Harvard's just supposed to be imagine or to take the movies, right? And like,
It's not
like,
easy.
campus, Brick buildings, trees.
Yeah.
But yeah,
So
definitely
it's just
like-
floating there. Now, I don't know how.
So I did make
So this
So try running without enabled solve there.
my app.
Do the same thing.
and then enable just delete all that.
Yeah. See if that'll catch it.
I don't know how to delete it when.
Because is it slow as checking those files? Include, oh, it's looking at just the, it's looking at add-ons. They have an ID straight? Let's see where it is.
That's it. I think the first point is just out and something. But I don't know what the point is. So I know that if I do the
Oh, what if you don't declare it?
if I do draw
It's a business name, but
Yeah.
so I try that. And then there's a problem because I don't know what the point is. That's something
I'm sort of curious, what if you run it directly on just that main.cpp file?
you try to draw it like a lot.
Just like main.cpp. I wonder if it is.
Yeah, when the computer science something's claimed that I did it perfectly, I'm just like, I didn't.
Let's see, and you are doing dash enable equals all.
Yep. I couldn't do dash. I just do one dash.
Oh, do two. Let's see if it makes sense. So, does it complain?
Yeah. I did dash and then it said
This is
man
basically
is
single
not
player
recognized.
because this one guy and
Can you look at, if you just type in CPP check, let's see if it gives you the help. And if you scroll up, it should have some examples. Oh, there's an enable all. Yeah, try running it like that. Yeah, with the exact example that it has there. So do the whole line except test.cpp will be main.cpp. There we go. I wonder if inconclusive is. Yeah, I think that maybe is more aggressive in
Okay.
like handling warnings and flagging those basically. Yeah.
We'll try running again with that.
Cool.
Thank you.
Yep. You're welcome. Yeah.
I finally go really quickly with Doctor for some nowhere. So like, I got working, I got rid of all the single SIM card stuff, and I think I'm sure there's enough like, to really, to use this
Yep.
separate CDS. So it's really good. So all the status is gone.
Yep.
And what I did is I just
Construct your house.
yeah, I've got structure and I have your function points. But what I've had to change is I used to avoid the effort to take in instance now.
Oh, sure. Yep.
So that's how I decided to solve it.
Okay. Yep.
And then take in whatever instance you create through local, I guess.
Yep.
So it should work with the other instances, but also apps.
Yep. Let's see. Solar symbol. Yep.
Yeah, and so it's working, but like I don't know if this is the direction to keep going. I just look for like kind of touch a couple like singleton, so
Yeah, I mean, again, yeah, that's sort of a problem with it. But I guess the way you'll know it's working is once you write your unit tests. So if you can write two separate ones and get two separate instances of app, then you're good to go.
right. So like I mean, if I create my instance here, I just call it instance.
Okay.
I could make them call it whatever instance two or app, whatever.
Yeah.
I'll just pass that into these. Or no, I wouldn't. This is work.
Yep, yeah. This should be good, yeah. So you can kind of copy this. One cheap way you could do is just literally copy this, do it another one. So as soon as you hit exit in one, it'll just re-initialize another one.
Yeah.
So you can show the place.
You create a function that like you pass an instance and then it's just that it calls all these functions there with the whatever it's passed into it for you, I guess, and that would be a way to do it. But,
Yeah.
so I guess this is okay.
Yeah. Yep. Yeah. That should be all. But you are right. There still are some problems with coupling, right? It still is a kind of echo class.
Yeah.
But we'll work on those later.
Sounds good.
Yeah.
Thank you.
You're welcome. Looks good. Yeah.
I'm going on Piazza, so and they can answer eventually. But just kind of something that CPP check brought up after doing the singleton refactor on assignment 4.
Yeah.
It said that it was like, you don't have a copy or copy assignment constructor declared for this thing, but if you do a decopy, it would just pop up a new window. Because you have to do like m window equals new window, which I think would just pop up a new window. So basically all my question was is like, would this be a situation where we're okay with a shallow copy and just kind of ignore the CPP check is yelling at us, or?
Yeah, I guess CPP check is basically, there's this rule that I think I might mention every time you do a constructor, you do like the rule of 3, then you have to do the destructor and copy constructor and copy assignments. I think that's the rule it's following. I would say it's still probably worth just defining those to get rid of it, and then if the copy ends up just being empty, that's okay. Or if you're implementing the shallow copy, that's fine too.
Okay.
So I think.
So I did that to read the shallow copy, and then it was like, this is only it said like you're only doing a shallow copy, and you're doing a deep copy.
Okay. Well, yeah. If it's a loop like that, then yeah. Static analysis may provide false positives. So
that's what I figured. I just wanted to make sure there wasn't some like secret way of doing something.
Yeah. I mean, as far as it goes from like a sort of, we might run CPP check or something, but we're not going to be like, oh, there's one missing minus one without, thinking about it. In fact, that's not even how we're doing the rubric, but, maybe we'll use it to inform us, but we would think about it, yeah. So good to know, yeah. Question? Yeah.
I want to talk about, probably talk about how to delete a pointer in Angular.
Sure.
So I added features onto that. So I drew like 2 million or like 3 million comments. Draws. And then I did my resource monitor.
So you had like a vector, a bunch of pointers?
Yeah.
Okay. Well, let's talk about that after the lecture.
Yeah. Okay. Yeah, but I cannot delete pointers, so I have like 3 gigs of usage. And it scales infinitely.
Yeah, so there's 2 strategies. One, you have to iterate through the vector and sort of delete if you just have a pointer. The better way to handle it, or a cheaper way, is to convert this into a shared pointer.
Shared pointer. Does it automatically drop itself?
It will once it's out of scope, yeah.
How about a unique pointer?
Same thing, yeah.
What's the difference?
Shared pointer, you can have multiple things pointing to it.
Okay.
Unique pointer, you can only have one thing pointing to it at a time.
So depending on my implementation.
Yeah. So actually, unique pointer is probably fine, but that's the fix here. Let's keep this unique for sure.
Thank you.
That should get your usage down, and then you don't have to manually free this because when you delete this object, it'll be out of scope and it'll delete itself, right? This will, when you're clearing your vector, this goes out of scope, so it's calling the shared pointer destructor, which is deleting the raw pointer inside. Yeah.
Okay. Thank you.
Yep. Yeah. I'm meaning to do another like YouTube on just like smart pointers or whatever, but that's all I need for now.
The only way I knew about this was because I purposely got my usage like 3 gigs.
Yeah.
And basically crashed my computer. And then I couldn't clear it.
Yeah. So yeah, this will save you because that's how I fixed it. Yeah. Alrighty, folks. Let me get us back in action here. Kind of get us to the final haul here. I see folks have mostly found their teams are fine. That's awesome. All right, so where we were looking at some TCP stuff, and still some mysteries here that we have to unravel with the networking part. So I want to look at sort of the programmer's view of a few of these things. Again, this is what's going on behind the scenes as part of our networking course, but what are these IP addresses that we always hear about? So basically what these are, right, it's a 32-bit address that is, it's an address, so it's just like your house or apartment, right? It's got some defined location as to where something is in the world. Okay, so depending on what these addresses are, they map to a actual, perhaps some router or some wide area network in the world. Okay, now how these addresses are sort of assigned, it's a little bit tricky, right? And they change too, right? They can be dynamic. So that's sort of a question maybe for networking or your internet provider, right? They're sort of managing some of this, right? So your IP at home will change on occasion. You can get static ones and these kind of things, but so for instance, Northeastern, this address happens to map to Northeastern here. So you can type in your browser. Actually, I should have checked before, but you can type in something like this in the Chrome, and it should bring you to northeastern.edu. At least whenever I did the lookup here. If it goes somewhere else, just be careful. And part of this, so there's also this sort of mapping scheme, and I'm going to show you a few of the actual C function calls so you can figure this out. But we as humans, we better understand www, worldwide web.northeastern, and then some domain here, .edu. Right, we don't want to remember this number. So there has to be some sort of mapping between name to IP address here. Okay. Now, when we know this address here, that's how we're going to tell our sockets where are you communicating to. So, for instance, if you want, you can try to connect today as soon as you figure out sockets to northeastern.edu, and you can start sending UDP or TCP requests and see what happens. You might get banned on your machine, so be careful. But that's essentially what we're doing, right? This is figuring out, again, the analogy of somebody's physical address and just sending them a bunch of mail. So there's different. Just a quick aside, you'll hear this term IP version 4 and IP version 6, so IPv6 and IPv4. That has to do with how many bits those addresses are. So I just showed you the 32-bit IPv4. But eventually we ran out of addresses. So we had to extend how big that address is. And that's what IPv6 is. Okay, 128 bits to store our addresses. So you've heard these things, Internet of Things, edge devices. If you have a smart fridge, smart TV, all these internet-connected devices have to have their own IP address. Okay, essentially. So we needed more. Okay, it's kind of like, I don't know if folks remember this, but I remember when my phone number used to be 7 digits and now it's 10. Right? We added an area code because there were more people, and then we had to make our phone numbers longer. I remember being very confused as a kid. I'm like, what's going on? So the same thing happened with IP addresses. So again, the programmer view of an IP address is just some 32-bit number, and so there's going to be some struct for this. This is actually what it looks like, an input address, which is an unsigned 32-bit number. Probably the more useful visualization is what's down here, but since it's just a number, you just take 2 of the hexadecimal values here, just kind of chunk it up into 2 hex numbers at a time, and that's the actual address. 128 corresponds to 80, 02 hex 2, and so on. Okay. So that's where you get that IP address from. Again, it's just an integer. Okay, so this wall of text here is basically starting off with what we talked about before, that clients and servers, right? We connect with a socket, right? And we can have sort of this point-to-point, so connecting 2 processes together, and that's what the socket does. We say it's sort of fully duplex, meaning I've connected this pipe, and again, if you remember the tin can example, you can both talk at the same time, and information will flow back and forth. Okay, so that's allowed. And then you can, of course, do this reliably if you're using a TCP protocol. Now, the other part to this, though, is our socket, again, is that endpoint, that connection. But we have an address, but we also have this thing at the end, so you'll see a colon and then a port. Okay, and maybe you've seen this on some websites that you've visited before. But the port number is kind of like, you've got your own IP address on your machine, but if we're all sharing the same network, we sort of want to know what door we want to open into. Right? So thinking that port is another word for a door that we want to open up. We can be a little bit more specific. So a port is just some other 16-bit integer attached to this that tells us, where we want to communicate. Okay, which specific machine. We want to talk to, this person. You all have sort of a unique port number. Okay. And what I'll also say is some of these ports also have well-established meanings. So again, if you want to think of a port like a door, port 80, for example, is associated with a web server. So meaning whenever you go to a website, you could put :80 after, right? Google.com:80. And that's sort of a request to that server for some information. Okay, how's the order enforced? Well, we learned about TCP. Okay, so here's some other well-known ports that you maybe have heard of. Port 7, we'll just echo back to whatever you're trying to request. 21, FTP server. Right, if you've ever downloaded something from an FTP location. File transfer protocol. SSH, right? We're familiar with this, Corey, right? So maybe you've seen a 22 somewhere. So whenever you're doing SSH at login.corey. whatever, you can append a 22 after that, and you're trying to just establish a connection, right? There's some other secret pathway where you want to communicate with Northeastern machines. That's through port 22, right? It's its own separate pipe. It's a secret hallway, if you want to think of it that way. So emails, web servers, etc. So there's different ones for different things. Let's see here. So here's an example. If you want to see on Linux where this is, it's in the etc. services. You can see the different port numbers and what protocol they're actually using. I don't think there's anything super interesting, but you can see some of the Echo, again, the 7, FTP here. Is both 20 and 21. So a few different examples there. Okay. So we've expanded a little bit what our notion of a connection is with a socket. So we have our client, where we're trying to, or our client address here, and where this connection is. So here's our client address. What port it is, right? Because I'm a different person than any of you, so I've got my own number here, 51213, and then our server where we're trying to establish our connection to, and then maybe for some service that we're requesting. 80 is just sort of like, give me this web page, for example.
So is this the line is able to know where it's supposed to go to?
Yeah, exactly. Yeah, so this sort of closes the loop on how do I know when I'm sending something from my machine that it's supposed to go exactly to yours and not just broadcasted to everybody, right? There'll be a specific port. number. Right.
And the IP address as well.
And the IP. Yep, this term. So we can also think of the port in our analogy of an envelope. Right, you write the address, street name, state, if you're in the U.S., zip code, and then the actual port number is when you write the person's name, because there could be multiple people living in a house, but the port is, to Mike or whoever. That's a little bit. I think that analogy works for what we're doing. Sometimes it could just be a service too that you want. All right. So here's a port for a specific service. 80 is the common one for a web server. All right. Another look at sockets. Just from the sort of programmer's view, again, sort of the Unix programmer, Mac, iOS, etc. We know what a socket is. I'm not going to run through this again, but you'll see FD is a suffix here, again, just because it's a file descriptor. That's all it is. We're just opening up some little secret pipeline to communicate between. And here is another view of what it looks like for a client server talking together. So we start with our server, and it's got to start up. And whenever our server starts up, it's just listening. It's saying, okay, is there anybody out there? Does anybody want to connect with me? It's just listening. It says, please, somebody. And the client launches. And then a request is made to that specific server. Okay, so we open up our socket, we have the IP address, the port, and we try to talk to our server. Now the server, when the connection takes place, this exchange happens. And, well, I should walk over here, is when the connection's happening, the server has to accept, so it has to make sure, okay, this is coming from some other IP address that looks safe. Okay, we know this is Mike's machine, or it's Mike's machine. He's banned, from this website or whatever. So there has to be some kind of handshake here that happens. And then this block is just essentially a loop of reading and writing data from these sockets back and forth. Okay, and then eventually a client can disconnect. And the server drops the client, whatever that means. So maybe that's deleting the sockets or some path or reopening that connection. All right, so here's our programmer view again of a socket, just if you're curious what it looks like. Sort of the, well, this isn't too interesting. It says protocol family, and it's always AF_INET, so something for internet connection. But there's a port number, there's an IP address, and then there's a bunch of wasted bytes here, just some padding that's left over. Okay. Just to unveil a little bit of the mystery here. How do we convert some number like 69, 59, 196, 211 to stackoverflow.com? We've got some functions for that. Get address info. There's a function here, and get name info. And these functions will sort of back and forth give you the, if you want the actual digits or if you want the actual name. So whatever you're providing, either way. So this one is address to name translation. This one gives you the opposite. Address to name, so this would be name to address.
Is that an operating system thing or a C++ thing?
This is just in C if you include sys/socket.h. Yeah. So there might be a program here. Let me see if I get adder. There is not. Yeah.
There's NSLOOKUP, which is.
Yeah, NSLOOKUP here. Let's see. Manual page NSLOOKUP. Query internet names interactively. Okay.
So you can do like NSLOOKUP Northeastern.
Let's see if it still matches. Yeah. Northeastern.edu. All right, there we go. It has changed, yeah. Don't click on anything. Yeah. And we'll also see, there's some other, okay, so Akamai is, the content delivery network or whatever. So folks have ever seen Akamai in Cambridge, they're responsible for routing internet traffic. Actually, it might be a really interesting company to co-op. I know they do take quite a few co-ops. But yeah. I forget all the other ones. There's like, let's see, NetStat, maybe is the other one. No, I don't have it, but yeah, NSLookup. Yeah, play around with some of those later. Okay, so again, you're going to see this a million times, client server. Maybe more for just reference, or it'll be useful later. But you can actually see, okay, for our client, maybe we want to get the address info, and then connect to some socket, right? I just want to type in connect me to www.northeastern.edu, not memorize some URL. So this will do the right thing for us. Okay, grab the address data, something like that. Create our socket, something like this. So here it is in C. We're going to avoid this. We're going to use just SFML. Okay. Server does the same thing. It's establishing a socket. Bind says, okay, associate server socket address to socket descriptor, so whatever our server address is. Then we listen and say, hey, is anybody out there? Connect to me, please. And then we accept, and we run through that loop again. All right. Let's see, we just had our break, so I'm going to keep moving us along here. So two other means of networking. I talked a lot about TCP and UDP today, because that's what we really care about. But again, just if you're curious, it's fun to mess around with. SFML does have a HTTP, what they call response and request class. If you want to practice, trying to visit some website and receiving information. This is actually how I do all of your, if you ever wonder how I push all your assignments to GitHub. GitHub has an API where I can request information from it. As long as I'm logged in with my token, I request a bunch of information about some classroom called FSE 21, etc. I say, okay, as part of that API, and then I put a little question mark with a little query thing in the equivalent of give me all the students, and that gives me all your names. And then I just kind of hack together a script to copy all the files to you guys. So this is kind of fun to play around with. You might have a use case for Paint to do this, so it might be fun to play around with. So that's on the HTTP side. Likewise, if you want to do stuff with downloading resources, maybe you want to create, this is going to depend on maybe what people have done on your team. Maybe they've done some more networking stuff, but you could have some database somewhere. Database could be a wide term here, but where you want to download files from or whatever. Okay, so FTP is also available. All right, but let's get into the SFML stuff, just to show you what's available and what's going to be in your lab. So, we have a few choices. And actually, I don't care so much what you use, but so you could use the C sockets if you want. Again, the good thing about them is they're portable. They're going to work everywhere. You don't really have to worry about anything. So that might be something to consider if you say, hey, I'm really excited about iPhone and want to do something with that. Maybe you'll have an easier time using sockets, but for the most part, I'm just going to point everyone to SFML's C++ wrapper around sockets. Okay, they've got some nice classes. You don't have to worry too much about all the nitty-gritty details in C. But you know them now, or where to start looking from the previous slides. So what this means is, previously you've been linking in, when you compile SFML-window, SFML-system, SFML-graphics. We haven't done anything with audio, but you'll also have to link in SFML-network. Okay, so we've got a fourth module here. This is roughly what it looks like. These are the classes. So if you go to the help page, again, you'll see those other protocols, FTP, HTTP, etc. But some other ones that kind of look interesting. Packet, so maybe a way to wrap up some information that you want to send. Socket, we've been talking a lot about those. But even better, there's something down here that's called TCP socket. So if you want to reliably transmit information back and forth, maybe that's a place to look. And likewise, UDP socket, if you don't care. Right? Whatever your team decides is important. Okay. The other reason I like ASFML, it does have pretty good tutorials as well. So on the tutorial section, just want to draw your attention. There are a few tutorials. The first two that are sort of important on just how to use the socket library, and sort of re-explaining some of the stuff that we've talked about in a short article about how to do networking with ASFML. Okay, so I'll point you to that. That's what your lab's based off of today as well. And from the actual documentation, here's a complete example of a client and a server here. Okay, it fits in one slide, which is kind of nice. I might recommend playing around with this. It doesn't do anything super interesting, meaning that you just start a server up, and then it just basically waits for our client to connect, and then it'll terminate. But that could be a very good place to just start from if you're building this. Okay. All right. So let me actually. I'm going to run your lab example, and I'll ask a few questions here. Let me show you what you're going to be doing here. And let's see. I'll just jump into it here. So you'll have your final project repository. Again, you'll go into the labs folder here. Everybody should have lab 8 networking. And there's actually a part 1 and a part 2. Okay. Let me just show the README here. So part 1 is doing TCP networking, and part 2 UDP. Okay, so we've got one example of doing either of them. Okay, so let me hop into part 1, and let me split my screen here. Okay, so what do we want to do here in part 1? Well, what we've always been doing, go into the bin directory, CMake, our favorite tool, and that built a make file here. So I'm going to run make. And again, you might have to do a little bit of toggling or whatever you've been doing. What's different about that CMake list file here? Let me actually open that up here. Let's see here. Just want to draw it to your attention. It's still building the tests here. But again, just make sure that we're actually including SFML network as well for both our app version and our test. It will be asking you to write a unit test at some point in your final project for networking. So you can actually think about that as well. All right, well, let's actually build it. All right, that's thinking, making me nervous. Okay. Otherwise, we were about to all go home. All right, so we have it running here. So this is the TCP example. This one actually should go smooth. UDP is kind of wild. But I'm going to go ahead and run the app here. The way I'm set it up, and this isn't production code, it's just for you guys to learn from, but you're going to enter S for the server or C for the client. Right? So it's all in the same code base. I'm going to need to launch the server first, right? So the left side is starting TCP server. On the right side here, let me go to my bin directory. I'll launch the same app here. Okay. It's going to ask, okay, do I want to be the server or the client? No, this time I want to be the client here. And join here. Okay. Now, as soon as I joined, notice that the server did something different. It said, hey, received some connection here. Okay, because the server was just listening and say, hey, is anybody on this IP? Is anybody on this IP? Now from our client, I think we can just say, hello. So you'll see the message come from the client. Hi. bonjour, whatever. So that's the sort of TCP. The server is not set up to send anything back or really do anything interesting, but so this will be an example of how to just start collecting some information. So I think in this example you might see how I'm collecting these messages in some vector or something very, very simple like that. Okay. Okay, so that's TCP here. Let me close that out here. Now the UDP example, let me just dive into it. It might break, and that's okay if it does, because I want to show you how to fix it. Let's go into part 2. Go into the bin directory. I guess I already built this one. Okay. So this time I'm going to run the app. Just to show you where I'm at here. Let me make sure I'm in the same spot. Part 2 bin. Okay. So this one's also in part 2. Got the app. So same process. Do I want to be the server or the client? The server first. This one asks me to set the port number here. And you'll have to be a little bit careful. Meaning that if I use port 80, well, that's a well-defined port, right? That's for other HTTP requests. If I use 21, that's also for FTP. And it's possible you have just some random port from some other application, right? If you have Dropbox running that's using some port, that you could get blocked. So I think 2000 in general has been safe for me. So I'm going to do that here. Okay. And let me go ahead and run this again here. So this time I want to run the client on the right side. I'll set up port number here. Now this one's going to be different for the client here. It's got its own communication channel. Because remember, the UDP isn't sharing a connection. I'm just spamming some address, right? So that's okay here. Okay, so I did this, and then I got a message. Somebody joined. So 127.0.0.1. That's actually a special IP address. That's your local machine. It's not something out in the World Wide Web, but it's just your local host. And then we can see the port that joined here. Okay. So should I start the server? Yeah, let's start it. Yes. Okay. So UDP server launched with one client. Hello. Hello to all clients. Okay. So in this example, I'm showing how to broadcast out a message from the server to all the clients that have connected. So I've sort of collected in some structure. I have clients. Let's call them 2001. That's connected here. Okay. And I don't think it's just have to Control C. I'm going to try this again with multiple clients. This might break, but it's kind of fun to do. Let's see. Server 2000. All right, and this is essentially how you're going to test, right? You can run the same process on your machine multiple times, and then eventually, you'll try to do this with everybody in your group somewhere. This is to be part 2.
Will this work over the internet address if we have someone's external IP?
It might. Where we tend to run into problems is folks' firewalls will block other connections, so you'll have to enable them to be safe. Usually what folks have done, and this is a great question, we'll probably have to debug this later again, but usually what has tended to work is folks will create a hotspot on their phone. Everybody connects to that network, and then they, nothing's blocked on that.
Shouldn't it work if you have all an NG?
It might, Northeastern might also be blocking a bunch of ports. So. Yeah. What's that? Yeah, Northeastern tends to be safe, which is good for us. Let's see if we can get. I hit enter. So this isn't a very secure app. Let me do it again. All right, you'll make yours a little bit more robust. Clients, 2001. Okay, we don't want to start yet. Client again, and it's got its own port here. Uh-oh. What did I do? Enter server IP. Oh, it might break here. Okay, well you have one that connects to one. One client, one server. I don't know what happened to this one. If you get some message like this, let me show you how to clean this up too. This is a thing I was trying to break. I'm not sure if it'll break the right way. If you notice that your servers and stuff are acting kind of weird, make sure that you've killed your processes here. So I'm going to grep for app. It looks like one of these is still running in the background. That might be taking up one of those ports. So on occasion you'll have to kill that process. And if you're on a terminal, you can sort of do it like this. You can grep for app and see if it's running. If you're on Mac, you can do the same thing. Windows, maybe you'll find it in the task manager. Okay. So that sort of created the issue that I want. To see that issue exactly, let me just show you here. And this is only, if you run into weird issues. There's a little video here saying, watch this for a little debugging mistake I made. That might be helpful. Okay, because in my actual walkthrough I make a mistake. So. Okay, so that's your networking code. Just to jump into it a little bit too, because I want to show you the code. And it's also part of that video, but I just want to show you the structure here. In the source. And it's all in the main in both the examples, both the UDP and the TCP. Okay, you kind of scroll through this. All right, we see all of our old initialization stuff. Basically, this is all the old, starter code that I keep giving you folks. But eventually, you will see a function that's just called TCP server, and this handles all the server stuff. That's just in one function here. And let's see. So you can see some of the, eventually you'll get down here. So within the server function, there's an infinite loop. And it's basically saying, okay, are we done or not? Otherwise, just run forever. And it's just listening for messages from clients, right? And you're going to collect the messages, and then you'll figure out, how to broadcast them out from there. Right? So maybe every time you receive something, you send something out. And then likewise, in both these examples, you're going to have a TCP client function here. So this was the first example. Setting up the client. Here's a socket. You can figure out the status. This is the size of the messages or the packets that you're sending out, just 2,000 raw bytes here, because we were just sending out text. The IP address you want to connect to. Special function here for just the local address. 127.0.0.1. And I'm connecting, so my connection by default always was 2000 for my socket. But for my actual UDP socket for me as a client was 2001. Okay. And this one was just a infinite loop here. Let's see, for the client to just keep sending out messages, and that was it. Okay. And then the actual body of the code, that first bit that you saw, both these code examples are roughly the same. There's a function called TCP network that's just running through that demo. So if you're the server, if you put an S, you execute the server function. If you're the client, you execute the client function. Okay. So that's about as bare bones an example as we can get. And it's probably not very good to leave your code in this state, right? So we probably want to think about, how could we wrap these up into maybe classes, encapsulate some of the data. So you can imagine the things that start going together, right? You have a socket, a port number, ability to send messages out, and so on. Okay, so a little bit of design for folks to think about, or maybe somebody will become the architect on your team for that part. All right. So any questions on the sort of lab stuff there? Your goal for the lab or the objective is going to be to show me that you got that running on your machine. So, I mean, you might finish that in like 5 minutes, right, if you can replicate. So I want to know that people can get it up and running so they can test. But then you're going to have to play around with it, right? That's probably not good code to base your final project off of. But you'll have something working. Right. All right, let me walk us forward to a question here. And again, this is getting to the little diagram we drew on the right here. How are we going to handle multiple clients connecting to a server? What do folks think? What programming tools might be helpful? Because again, a socket's just sort of a one-to-one connection. So structure-wise, what might you want to do if you want to handle multiple clients? Right, you saw my code sort of break. It can't really handle it. There wasn't really any logic. I tried. Didn't work.
Maybe like a hash map kind of a thing.
Oh, a hash map, okay.
Like with a key you connect to a particular server.
Yeah, so our key is maybe whatever the client is that's trying to connect, maybe from what port, or maybe they have a name or something.
Yeah, kind of an identifier.
Yeah, so we need some identifier, right? Some collection to store it in, so hash map, vector. Hash map makes it unique, right, so we can look up. Then maybe our server can kind of iteratively listen for all of them for every 1 millisecond or something. Yeah. Other thoughts for folks? Yeah. Yeah, so kind of was for doing TCP every time. I mean, you just add 1 socket for every client, right? Yeah. So we could have a vector of sockets. Yep, that sounds reasonable. Yeah.
Do some sort of like asynchronous touring for the server, so we'll follow that with.
Yeah.
There's a bunch of
So they can get.
messages.
Yeah. I don't know if I did. I don't think I've shown thread or async or anything here. But yeah.
So yeah, I think it's like threading.
Yeah. So we can have an asynchronous thread that's sort of listening for anything.
I was just gonna say fork a new process or run it on a new thread.
Yeah, new threads, new processes. Would be options that work. Yeah. Yeah.
I would say like also, would you also vector and have a vector for UDP?
Yeah, for UDP, yeah, we could still have a vector. I mean the same idea. Yeah, listening to each of the clients by some identifier. Right. So maybe every packet that's sent out has the identifier of who the user is, what action they did. Yeah, these are some good ideas. I mean, these are the things you'll have to sort of put in. So again, having multiple threads. If you can do that asynchronously, that's even better. But right, my server can spawn multiple threads, so I might have to review some C stuff. We talked about threads from 5008. I'm happy to show some examples too if folks want to ask about, just starting in C++. It's actually pretty elegant, pretty nice. There's also this thing called a socket selector. It's another one of the classes in SFML that allows you to just have 1 socket, and it does this multiplexing, so it can act as multiple sockets. Okay, so I'll just sort of point folks there. So either using multiple threads, the socket selector, or maybe just creating a bunch of sockets. We'll add that as an option. Or maybe just create sockets and do some bookkeeping, right? And that could be with a set or some sort of map data structure. Okay. All right. So let's run today's lab. Though we already did that. We ran it. Okay. Words to the wise. What did I include here? So the lab today is probably not too demanding time-wise, like you mentioned. You could probably do it in a few minutes. You might have to wrestle with your CMake a little bit. That said, think about these things with your team if they're here. whether you're finding them for the first day or if you want to just use this time, if you don't see your teammates, to write a message on Teams and say, Mike said we should think about networking. It's a good time to talk about it, right? And think about TCP versus UDP. How might you handle multiple sockets? I mean, even before you get there, just say, hey, let's try to get it working, on one person's machine or whatever. The other thing you'll have to think about too is, what information are you sending? So I showed how to send, raw bytes, which are just characters. But what about, a pixel? What information are we sending if we want to draw somewhere? Okay, so in SFML, you actually have a data type for that. It's called SF packet. It's an SF namespace. It's just called packet. You can actually use inheritance, one of our tricks here, to make your own packet. So it is a type of packet, so you can do all the packet things like sending them and receiving them. But you'll have to think about what data you're putting in those packets. Okay. What information would you minimally think you'd want in our Paint app?
Like X and Y coordinates, the color of the pixel.
Yeah.
Those two things for like the bare minimum.
Yeah. X and Y coordinates for painting and what the color is. In fact, you might be able to do the whole project just sending those back and forth. Depending on what operations you support, like if you want to do like a flood fill or doing different brushes might be a feature that you want to do. Maybe there's different ways to encode those, but we could just send a bunch of pixels. Yeah. That would be where I start. All right. I think that's all I got for you folks. We have an in-class activity for your lab time. Introduce yourself to your teams if you haven't. Say hello, and then I guess you can leave whenever your teammates are happy with you leaving or whatever you decide. That's all I got. I'm going to hang around for questions and for the lab.
Team 3, let's go.
So a question about the project.
Yep.